Okay. Good afternoon, everyone. So today is the ninth week of the interaction session of this course, Reliability-Based Structural Design. So my name is Devashish Panda. I am a Prime Minister Research Fellow at IIT Guwahati. So for this course, I have been allotted as PMRF TA, and every Sunday we meet from 3 to 5 p.m. We discuss the topics related to the current week. We solve different kind of problems using pen and paper and also using MATLAB, and then we provide all these things, including the MATLAB scripts for your reference. And so today we will actually go through the meta model based reliability analysis, where first we will spend some time on least square approximation, recap the concept. We will develop the algorithm, solve different kind of problems, and then we will move to response surface method, where we will see how the actual limit state can be replaced by a response surface, and we will solve different reliability problems using MATLAB. So we will basically going to code it and we will solve different problems. Then if we have time, we will discuss the orthogonal polynomials. Okay, so let's quickly start today's session. Meanwhile, other will join. So recall during this course, so before going to that meta model based reliability analysis, first let's revisit what other reliability methods we already learned during that course. So first, actually we have learned the gradient based reliability analysis. Gradient based reliability analysis, where we solve different problems using first order reliability method, considering the concept of Haushofer-Lind reliability index beta, that means the minimum distance of the limit state in standard normal space from the origin. And then we solve problems using Brightung and weight approximation for the second order reliability methods. So then we during the last interaction session we have gone through the simulation based reliability techniques also. Now let's find it out the question, or let's try to answer this question, why we need to go for meta model based reliability analysis while we have gradient based and also simulation based reliability techniques, and we already have learned this. So recall, in gradient based reliability analysis, what were the steps or what we need to do to perform an gradient based reliability analysis. So first we need to have a gx, that means one limit state function, and the limit state function should be defined with respect to the basic variables. That means that should be defined explicitly. Now we convert this limit state or transform this limit state into gz, that means standard normal space. Then we evaluate the gradient of this limit state function. That means that will lead to the optimization problem, and we already have solved using Lagrange multiplier technique, and we find out the reliability index beta and corresponding probability of failure. Like, we start with some initial beta and some initial direction cosines, then we will uh, you know continue the iteration until the convergence will achieve. Now the thing is, if we want to apply the gradient based reliability analysis to some problems, we need to have the limit state function in explicit form. That means that should be defined with respect to the basic variables. Otherwise, we cannot find out the gradients, or we can say the first and second derivative for the gradient based reliability analysis. Now the thing is, most of the engineering structures like buildings, bridges, we generally model using or with the help of that any finite element software, that means in finite element framework. So many times we may not have the limit state in explicit form. That means the limit state shouldn't be or may not be defined completely with respect to the basic variables. Like, if we have a building, so this building has modeled using Say for example, this building is modeled using NCS space claim. Now we have the model, finite element model. Now we want to find out the reliability of stress of this node, particular node. So we can formulate our gx like that. Gx is equals to, for this node, sigma allowable. That means actual stress which is induced in this node, that means allowable load first, that is your capacity. That means that allowable thing will come from the code or IS provision, or the standard you are looking for. Now minus this actual stress which actually generated in this node. So this sigma may be the function of EAI, but this is not explicitly defined with respect to these terms. So how we can perform the reliability analysis of this structure, or say for example, for this node we want to analyze the maximum deflection. So the GX might be in the form like del allowable, the allowable deflection, minus del actual. So for this type of problems, how we will proceed for the reliability analysis, the big question. So we can proceed, or we can perform this analysis using simulation based technique, what we already have learned during the last interaction session, like Monte Carlo simulation. We can use Monte Carlo simulation for this analysis. How we can perform this Monte Carlo simulation for this analysis? Like, we need to generate the samples of the EAI, whatever the random variables we have. Then we need to analyze this whole structure using that finite element software where you have modeled it, or using which you have modeled it. Now get the values, like for E, for one sample of E, we will get sigma. You will get 1 gx. For second sample, you will get another sigma. Then you will get another gx. So by this way, you will perform, and you can check how many times your limit state falls. That means your gx is less than equals to 0. And then you can find out the probability of failure is equals to the number of failures divided by total number. But this process will consume much time, because we need to generate much number of samples, to converge the results. We have already seen how the number of samples will affect the error in our estimations of our using that simulation based technique. So the thing is that we should have, or there is some method by which we can actually perform the reliability analysis, where the the limit state function is not explicitly defined. That means we have implicit limit state function. So for this purpose, what we can do, we can use a meta model or a response surface to replace this actual limit state. So in meta model based reliability analysis, what we generally do, if we don't have the limit state in explicit form, then the implicit limit state is actually replaced by or proposed by one meta model, and then we perform some analysis or steps we will see to fit that meta model to the GX and perform the rest of the reliability analysis. Okay, so the basic aim is, if we have, or when we have that uh, the limit state is not in the form of explicitly, or not defined in the form of explicitly, or we have the implicit limit state, we use, or we can use the meta model based reliability analysis. So that is the basic concept of the meta model based reliability analysis. Now let's first, you know we have like a response surface method to solve the meta model based reliability analysis. But before going to response surface method, we will spend some time on least square curve fitting approach, because that response surface method is basically the principle of that, basically based on your least square curve fitting approach. So we already have some knowledge about curve fitting and least square technique. It's a basic statistical method. So what is that least square curve fitting method tells? Like it's a statistical procedure to find out the best fit for the data points. Data points, that means if we have some observed data, so for that observed data we can find out the best fit using the least square curve fitting method. And this method, the basic principle of this method is it minimizes the sum of square of the residual. Now residual or error between the observed value and the proposed value. So let's quickly go through the concept. Like if we have the data points xi and yi. So we have the data points. So here we plotted like blue lines. Here this blue dot or the green dot, sorry, the green dots are the actual observed data. Xi and yi. We have the observed data from some experiment or something. Now we want to fit some model or fit some polynomial for this data set. So let's say we are first looking for that linear polynomial. So we have the polynomial function, like we can have the polynomial function f of x is equals to a naught plus a1x plus a2x square and up to the degree n. We can have the polynomial. Say for example, we wish to fit first linear model. So our polynomial will be the f of x will be a naught plus a1x. That means we are considering up to the degree 1. Now, so this is actually, look at here. So this is your observed value and this is actually the proposed value. So what will be the error? The error for this data point will be nothing but yi, that means the observed value, minus the value proposed by or proposed using this linear model f of x. Now what will be the sum of square of the errors? Now we need to square the error. Why we need to square the error? Look here, we can have the error in the term of negative or positive both. So in the calculation or while doing the estimation or during the estimation, we need to have these errors, absolute errors. That's why we square them up. So what will be the square of the error? It's nothing but yi, that means your observed data. So here up to m data points are considered. So yi, y1 minus f of x1 square and so on. So we can have the error square. Now sum them up. So this is nothing but s is equals to sum of square of error. So we can easily find it out, the sum of error of square of error. Now, the main principle of the least square curve fitting technique is to minimize this error. Because look at this, if we can minimize the error, then our approximate function or the fitted function will be more accurate, right? So our task is to minimize this error. So here we have the error, like we have considered here straight line fit. That's why we have considered up to the first degree of the polynomial. So up to here we are considering. Now this is the error yi, this is the observed values, this is the first order linear approximation or the this straight line fit f of x is equals to nothing but a naught plus a1x. So and some square of this is the error square and sum them up for this m data points, we will have the square. Now to minimize this or to get some minima, what are the criteria? First criteria, you need to differentiate that function with respect to the basic variables and equate to 0. Also you need to check that second order derivative should be greater than 1. So here we have two unknowns, a naught and a1. So what we need to do, we need to differentiate this s with respect to a naught and we need to equate it to 0 first. So if we do that, we'll get one equation. Okay. Now second, we need to differentiate this error sum of error square with respect to a I. So here only we have a1, so we will need to go for 1. So if we have general term, then we can have I also. So here only one term, so only one I will be there. And if we do that, will lead to this equation number 2. Now what we need to do here to get that, fit or that curve. So we need to solve for the unknowns. Here, what are the unknowns? Here we have two unknowns. One is a naught and a1. So we need two equations to solve these two unknowns. So these are the two equations to solve. By using these two equations, we can solve this a naught and a1. Here you can see the a naught and a1 have been solved. Okay. Now the thing is, these equations are called the normal equations. Normal equations. Now, once you have the normal equations, you can solve for a0, a1 and you can get your f of x. Is nothing but a0, you will get some value of a0 plus a1 into x. That will be your fitted function. The concept is very simple. You need to find out the square first. You need to find out the error first. Error between the actual or observed values and the function. Then square the error, sum them up. Now the main task is to minimize these errors. So to minimize this error, we need to differentiate this function with respect to the unknowns and equate to 0. And we will get that much of simultaneous equations. And these are called normal equations. And normal equations can be easily solved and we can find out the a0 and a1 values. Now you can, the task is to solve the unknowns. That means first you need to generate the normal equations. So here we have two unknowns. So we need two normal equations or two equations to solve the problem. Now if we have nth order polynomial, so we will have nth degree polynomial, then we have n plus 1 number of simultaneous equations. So let's see, like here, first we can solve one example also, then we can move to this. So first we can solve one example, then we move to the nth order polynomial. So here we have that data set, temperature versus length, and of a rod. So if we wish to fit this function L naught equals to, that means a linear function, L equals to a naught plus a1 t, find out the value of a naught and a1. So what we can do, so we have these data sets. With respect to temperature, the increase of length are recorded. So we have this data set. Now, what do we need to perform? First, and we wish to fit this linear model to this data set. So what do we need to do? First, we need to find out the error using this. That means nothing but your that yi minus this function a naught plus a1 x you can consider is like t. Now square it, sum them up, you will get the sum of square of errors. And now differentiate with respect to a naught a1, you will get the normal equations. Now here you will have two unknowns, so you need to generate two, or you will get two normal equations. Now here I will tell you some tricks, like you can easily generate this normal equation. Like here you have only the linear fit, that means L equals to a naught plus a1 t. So here you have two unknowns, so you will have two normal equations. So first thing, the first equation will be the coefficient of a naught, look for the coefficient of a naught 1. So just multiply the all the side with 1 and sum them up, equals to summation of a naught into 1 plus summation of a1 t. So the first equation will be summation of L equals to nothing but a naught n is the number of data points, you can replace it with m also, plus a1 summation of t. Now the second equation will be the term with a1 is t. So you need to multiply with t both side and sum them up. So summation of lt equals to here a naught summation of t plus a1 summation of t square. So to solve these two equations, you just need to solve these two equations to get a and a naught, that means a1 and a naught. So you need to find out the summation of L, summation of LT, and summation of T square. So you need to make a table. Generally, you can perform it using Excel, or I prefer MATLAB. Just make a generic algorithm and perform this. So we precisely will uh, perform this exercise. So first, so make the column. This is T. Summation of T give you that 300 value. This is L. Summation of L give you that value. Summation of T square giving you this value, and summation of TL giving you that value. Because to solve these two equation, we need the summation of TL, summation of T square, and summation of T, summation of L both. Now put all these things, you will get these two normal equation. 1, 2. Now if you solve them, you will get A0 and A1. And now fit your that curve. That means this is nothing but y, or here your L equals to A naught. The value is coming as 799.34 plus A1, the value is coming as 0.0297 into T. So this is the curve. So you can see that okay, we are using that data point. If we go with the linear curve fitting technique, okay, this is also fitted. Or also, although this data are the random data, we can collect different kind of data and we can check. So the main logic here is you need to find out the normal equations first, solve them, look for these constants or the unknowns. Once you have the unknown, you can generate the polynomial function, and once you have the polynomial function, you can fit your proposed function to the data. So let's see for the generic case, like if we have the nth degree polynomial to be fitted. Now nth degree polynomial, like f of x is equals to a naught plus a1 x plus a2 x squared and plus an x to the power n. So this is the nth order polynomial. So if we have nth order polynomial, we can also fit it. So what will be the sum of square of error? So nothing but yi. These are the observed value, and this is the nth order polynomial what we wish to fit within that data. So already we have the SSE, sum of square of error. Then what we need to do, we need to differentiate with respect to the basic variables, and we need to generate that n plus 1 number of normal equations to solve the unknowns like a0, a1, a2 to an. Now once we have these values, we can easily fit the proposed function to the data sets. Now that precisely have done here. So this is here. Now in matrix form, if we wish to write it in a matrix form, because when we will you know code it and want to solve this using MATLAB, what we need to do, we need to make a generalized function file. So for the nth order, if we wish to write in a matrix format, what will be that? So this is nothing but your A matrix that contains the summation of x. That means the first value will be x to the power 0, then summation of x to the power 1, summation of x to the power 2 up to x to the power n. And similarly, if we go this way, we will have these values multiplied with your unknown coefficients like a naught, a1, a2, a3 for nth order of polynomial. So these are the unknowns and these are the right hand terms. This. So in matrix form, if we wish to write, if this is we uh, write it down A, and this is nothing but say unknowns A is equals to say B matrix. Or here we have used different notation, you can also use the different notation. So how you can easily find it out, the unknown, this is A contains the vector of the unknown coefficients. So that will be nothing but your A inverse of B. So when we will code it and try to solve different problems using MATLAB, so we will code in that way. So how this matrix are have we have generated, I hope you understand. Like for the nth order, we just separated out the coefficients and the terms with the coefficients. Like if we wish to go up to the second degree, so how many normal equations we have? Like first normal equation will be summation of y is equals to a naught n plus a1 summation of x. Now the second equation will be summation of x y is equals to a naught summation of x plus a1 summation of x square. Now the third will be summation of x square y equals to a1 summation of x square plus, sorry, a0 summation of x square plus a1 summation of x cube plus a2 summation of x to the power 4. Now this is nothing but your this right hand side equations. Just look at this summation of y x to the power 0 into y for uh, I equals to 1. For I equals to 2, you will have xy, because for 1 x and y you will have. For x equals to 2, you will have x square y, and this is the left hand portion, the entire part. This is the left hand portion. Like for the first a naught term, you will have x to the power 0, that means 1. For a2, that means for a1 term, you will have summation of x, that means this value will be summation of x to the power 1. And simultaneously this will goes up to, we can see that goes up to x to the power n if we have nth degree of the polynomial. That means we need to solve nth number of simultaneous equations. So by this way, this matrix formation have been done, and we will precisely use this formation to solve or to code to generate the function file in MATLAB. Great. So this is the concept for the least square approximation. It's a very simple concept. Just find out the error, square them, sum them up, minimize the error, find out the best fit. That's all. Okay. So like we will solve these two problems using MATLAB. Just wait for sometimes we will go to MATLAB and we will code the whole algorithm and we will solve it. So the concept is clear. Like if we have data set, we can fit different polynomials to that data set. So for that we need to generate the simultaneous equations to solve for the coefficients, and then we solve it and generally, you know, replace that or fit that polynomial to the data set. Okay. Now we can also fit different kind of like functions to the data set. Like if we have the power function, if we wish to fit the power function, we can also fit the power function like y is equals to a to the power x. Take the log on both sides, simplify it, you will have the model like this. Again, you need to generate the normal equation, solve for a naught a1, you will get your polynomial. Now now like this problem here, already we have seen that if we wish to fit a second degree uh, polynomial to this data set, what we need to do? So up to second degree polynomial, that is represented by a 0 plus a1x plus a2x square. So how many simultaneous equation or normal equations we have? We have three. How we can formulate them? So either you can go with the first, you need to calculate the error, sum them up, square them, sum them up, then differentiate this with respect to the basic variables. That means here we have three variables, so you will get three equations. And what I said, to generate this normal equations, just what you need to do, just remember that tricks. The first equation will be the coefficient, like so here you can write y is equals to this, f of x, I am replacing that y is equals to this. That means this is your dependable variables. Now, first equation will be summation of y into 1, the coefficient of a naught, and sum them up is equals to summation of a naught plus summation of a1 x plus summation of a2 x square. Just multiply it with 1. That means we have the coefficient of a0 is 1. Now the second equation will be coefficient of a1, that means x. So you need to multiply both sides with x and sum them up. Xy is equals to a naught summation of x plus a1 summation of x square plus a2 summation of x cube. Now what will be the third equation? What is the coefficient of a2? X square. You need to multiply with x square. So x square y is equals to a naught summation of x square plus a1 summation of x cube plus a2 summation of x to the power 4. So these three equations you need to solve. So you need to have the summation of y. So you need to make this table for the calculation. So x and y, these are the given data points. So summation of x will give you this, summation of y will give you this. Now summation of x square, why we need x square? Because to solve this equation you need to have the summation of x square. So summation of x square is this, summation of x cube this, summation of x to the power 4, because we need to solve x to the power 4, or we need to have the value of x to the power 4 to solve the third equation. And summation of xy, summation of x square y. Summation of x square y, why we need this? For this equation. Summation of xy, we need this equation. Now, put all these values to these three normal equations and you will have these three simplified equations where the unknowns are there like a naught, a1, a2. Now solve these three equations, you will have a naught, a1 and a2 value is like this. So this is your final polynomial which we wish to fit here. And here we have seen that okay, this is the polynomial function. Here we have fit, and we have seen that okay, that give us some good fit also. So what we do actually generally we will do now, we will make a generalized function file for these data sets where we can handle the nth degree of the polynomial. So let's quickly go to MATLAB and quickly try to code it for nth order. Like we also have different kind of fitting techniques. Like here one example is given. If we have to fit a power function or exponential function, what will be that? So the basic concept is very clear. You need to have these functions or the polynomials you wish to fit for the data, find out the error, find out the square of the error, sum them up, minimize it. You will find out the normal equation, solve these normal equations, you will find out the coefficients, unknown coefficients. Once you have the unknown coefficients, just form your polynomial function and solve it. Great. So here like one nonlinear function or continuous function is there, we will not discuss into it, but we can go and we can fit different kind of function also. So weighted least square approximation, we will come into that. So least square approximation, this concept is clear how this least square approximation is done and how we wish to fit or how we can fit one data set or one polynomial function to the data set. So let's quickly code it and let's check how these results will or how we can fit or how these results are coming. Okay, so let's go to the MATLAB editor and let's quickly code it and solve some problems. Then we will go to the response surface method where we see that how the meta models are used to create that to replace that uh, response surface or the original limit state method, original limit state, and we can perform the reliability. So let's quickly go to MATLAB and we will code that least square approximation and we will move forward. So just 1 second. Okay, so what do we need to do? We need to you know perform this to get the unknowns actually. And our main task is to code that. So what we will going to do? So first, what we need to do? We need to load our data set. So here we are loading the data sets. Let's see, we will solve this problem, this temperature problem, what we have solved here. So data set, we will take this data set. So we will come to it later on the data set portion. So first, what we need to do? We need to have the data, x data. That means you need to load your x observation points and y data. So these are the input files. Now here I have used one function which actually control the you know the degree of the polynomial you wish to fit. Like for 1, it will fit, or it will go for the linear fit. If we put 2, it will go for the parabolic fit, and 3 and so on. We can move up to nth order. Okay, so the n is the length of x, that means the length of the data points we have. Now what we need to do? We need to create the A matrix. A matrix, that means this. Here we can see this matrix, right? And what this matrix actually contains? The terms with the unknown coefficients. So first term will be summation of xi to the power 0. That means nothing but 1. Second term, summation of x, summation of x square. We have seen that if you write in number of normal equation and arrange them in matrix form, you will find it out like this equation you will get. So what we need to do? We need to find out this A matrix. A is nothing but this. So look, precisely this step as done here. So for I is equals to 1 to n and jj equals to 1 to n, because we need to create that matrix. So first, summation of x to the power I plus jj minus 2. That means when we will consider 1, I equals to 1 and jj equals to 1, what will be a value, or the component of a will be nothing but, what will be that? X to the power 0. Now when we consider I is equals to, or jj equals to 2, it will give us square, and so on. So in this step, precisely this part of the A matrix, or the complete A matrix, is formed. Okay, now we need to form this B matrix, and the B matrix contain x and y term. So first term will be only y, second will be x into y, that means x to the power 0 into y, and so on. So this vector will contain the part, or the left side part of your normal equations. So here we are precisely doing that. So for kk equals to 1 to n, sum of x to the power kk minus 1 into y. So when we consider kk is equals to 1, that means the first term, that will be x to the power 0 into y. That means only y. Here x to the power 0 into y. Second term will be summation of x into y. Third term will be summation of x square y. Fourth term will be summation of x cube into y, and so on. So look, precisely here in this step, that thing is solved. Like first term, when we consider kk is equals to 1, it will give you x to the power 0 into y. 2, x to the power 1 into y. 3, and so on. So we already have formulated A and B matrix here. For the nth order polynomial, this is your A matrix. We have formulated A, we have formulated B. Now we need to find out this, the unknown coefficients. So the unknown coefficients will be nothing but, say the unknown coefficients A will be nothing but A inverse of B. So we need to invert it. So here look, C, here I have considered C, you can consider A also, is equals to A inverse of B. That means C's are stored. Now once we have the unknowns, we can plot, or we can create our polynomial function. Now, using that solved coefficients, we plot the polynomial function and also feed the polynomial function. So let's see that our code is working well or not, whatever we have made. So like we need to have some data point. So here you can load the data through Excel or through some other like here text file, or you can read your data as per your convenience. It's up to you. Now let's see. we have some data points. So for the, let's see, for the this problem already, the problem already given in your PPT. Here the temperature problem. Okay, so here we have 6 data points: 1 2 3 4 5 6, temperature and length. So just load this data x and y. Here I have loaded it: 1 2 3 4 5 6, 6 data points we have. So x, first column will represent your x, that means see here for this thing the t, and the second column will represent the l. Now let's run the code. So first it will ask for f, which order of the polynomial you need to fit, or which degree of the polynomial, sorry, which degree of the polynomial you fit. So let's see, for our example we fitted the first order. So here look, it gives you the fit, also the polynomial values. Like this one is your a naught 799.3, and this is your a1. And precisely look here, a naught the value comes as 799.34, and the a1 comes as this. And the fit, if you look for the fit, you can see we have this similar kind of fit. Okay, now this function file is generic. Like if you wish to fit the second order polynomial to this data set, what you need to do, you just need to here give the input like I wish to fit the second degree of the polynomial. So second degree of the polynomial, just put 2, hit enter. Now you can see this is your second order polynomial fit. Now you can check which fit is the best fit and all these things, and you can conclude as per your observation. Now quickly recap like what we actually done, that least square approximation. So here in least square approximation, we have first we have a data set to which we need to fit, or we need to, or we wish to fit some model or some polynomial. So for that, the theory behind it is very simple. First, you need to find out the error between the observed data and the model you wish to fit. Square the error, because we need to have the error or absolute error, or in the terms of absolute error. Then sum them up, then minimize the error. Now doing, when we do the minimizes process, we have the normal equations. Now if we solve the normal equations, we easily have the value of coefficients. Now once we have the coefficients, we can easily formulate the polynomial function which we actually wish to fit to the data. And here precisely we have done in this code. So using this code, just what you need to do, you just load your data and just check which degree of polynomial gives you the best fit to the data. So it's a generic code. I will upload this function file to you. So what it does, actually first load the data. Here I have added one function or one parameter to control the degree of the polynomial. Now formulate the a. What is that a? Is nothing but the terms with the unknown coefficients, or we can say the left hand term of the normal equations. So if we have n degree of polynomial, we should have n plus 1 number of normal equations. If we arrange them in a matrix form, you will get this kind of matrix multiplied by the unknown and x. So the operation is very simple to find out the unknowns. Either you can solve for these equations or directly you can invert this. That means your unknown coefficients will be nothing but A inverse this multiplied by B. So the concept is very clear. So now let's move to another topic like weighted least square approximation. So least square approximation we have seen. So you also have you can also check different kind of problems. Like for this problem, this is one also one problem. You just load this data and check whether this function file will working properly or not. Just put this data there and just check. Here we have second degree data set. So let's quickly check. We have only 6 data sets. So let's check whether like this function file is generically working well or not. Like, so let's quickly load this data. Like how much we have. 2, 3.2, 4.1. So you just need to load it. So here like instead of this 2 and corresponding to 2 we have 4.3, 4.3. Now the second data set 3.2 and 4.5, 3.2 and 4.5, 3.2, 4.5. Now third and fourth data set we have 4.1, 8.2, 4.1, 8.2. So just put here 4.1, 8.2, 4.1, 8.2. Then we have only two like 5.15, 10.3, 6 and 14.4. So 5.15, 10.3, 5.15, 5 and 10.3. 6 and 14. So we only have 5 data sets, 6 and 14. And let's check whether our this function file is working well or not. Okay. So we have load our data. So you have large data set. You will either have the text file or dat file or Excel file. Just read that file and load it. So I am loading this data from this text file. So here let's check. We already have load the data. So we wish to fit the second order polynomial here. So just put 2, enter. Yeah, we are having the fit. Now let's check whether the PPT and these results are same or not. So here we can see the polynomial is like a naught value is 6.18, a1 2.2 and 0.6, and this is the fit. So let's check our results. Yeah, the fit is almost close. And regarding the results, we have almost like for this order like we are having similar kind of results like 14.4. The little bit of difference in data, like here 14.8 was the data. If we replace 14.8 we will get the exact curve. Wait a minute. 14.8. Yeah, so you just need to load the data, check it. whether you are giving whether you are getting the results correctly or not. And I hope you will get the results correctly. So loading the data here, like, oh, okay, it's 2 2. 1 second, it got up to bias. So you can fit up to any order like 4 5 6 7. You can go up to any order. This function file will give you any order like 2. I only 2. Yeah, so this is the fit actually we are having, and this is your polynomial. So you just need to check it with your data points, and you will get the values. Like if you wish to put uh, or fit the first order polynomial. So let's see, if we wish to plot the first order, how much it is giving. Yeah, this is giving the results, and so on. So you can control your data sets from here. Okay, so how many data and data sets, as per your data sets you can fit your polynomial using this function. So I am undoing this data, so that the actual this problem, the first problem whatever we have solved for this, we are getting the same results. So here we have the polynomial equations, and using this we can fit our data sets. Now come to the next topic. Like here we have seen that how to fit that model to our statistical data. Now we have actually another kind of, this is the ordinary least square method. Now we have different kind of we can have the different method like weighted least square method. We will spend just a little bit of time here, then we will move to the response surface method. So weighted least square, it's similar to the least square method, but we impose some weight to the particular points to get the better fit. Like here we can have, like we can see, this was the error. If without the weight, this is the weight, and this is the actual square of the error. So here we introduce some weight to the particular points to get the better results. Now rest of the calculation will be same, just one weight will come before that. So here for the first order equation, we have this as our SSE, where there are two unknowns, a0 and a0 are there. Now if we minimize this, what do we need to do? Or for the getting the minima, we need to differentiate with respect to a0, and also we need to differentiate with respect to a1, because we have two unknowns. Now once we have done the differentiation, we will have these two normal equations, same as previous whatever we have seen. And if we solve these two equations, we will get a0 and a1. And once we have this a0 and a1, we can have our actual polynomials. So here we can look into this example and see whether introducing some weight to the particular points, we are getting the more accurate results or not. So we will investigate that matter using this example. Like we have this set of data points. Okay, now let's consider the previous data sets. Already that previous data sets is given. Now for the data point 5 and 12, here you can say for the data set 5 and 12. Now this point 5 and 12, this point, for this just introduce one weight, that is 10. For the rest, just apply the same weight. That means these weights are actually user defined. Or you can vary this weight. You can put different weights on different points to get the exact values or the exact fit. What do you wish to find it out, and all these things. So here we have seen that first, when we solve using ordinary least square method, this was our fit for the first order for linear fit. Now when we introduce the weight, the red line, we can see weighted least square method, we have seen the better fit. That means the red line will go or pass through this point. So this is simple, just one weight you need to introduce to the least square method. Now using these weights, you need to verify whether you are getting the best fit for this approximation and not. So here all the calculations and equations will be same. Just you need to put one weight, the values of weight, and also the points where you need to introduce that weight. That is completely on the users who are performing this to get the better fit. Like here we are introducing the weight 10. Now instead of that 10, if we wish to introduce higher weights here like 100, we use 100. Here we can see that okay, for this point we are getting the better fit. That means introducing some weight, we are improving the fit. Whatever we have get from the ordinary least square method, we are actually modifying the results or getting the better fit. So that all about least square approximation and all these things. But our task is how we can use this concept to the reliability problems. And so these are like general forms. If we go up to nth order, and if you have the continuous function, if you have the continuous function, instead of summations you need to integrate these functions, and all these things you can easily solve them up. Now our goal is to, or our main motto is to, how we can use this concept of curve fitting to the reliability process. So we have the response surface method. So in the very beginning, what we have discussed, that if we don't have the limit state in explicit form, or if the limit state is not defined explicitly with respect to the basic variables, we cannot perform the gradient based reliability analysis. Because if we don't have our gx with respect to the basic variables, we don't find out, or we can't find out the gradients or the derivatives of the limit state function, right? So for that, what we need to do, we need to first formulate one response surface or a meta model, which will be the replica or the nearest replica of the limit state function, and then we perform the rest of the reliability analysis. For like this, for this bridge, if we have the gx like for here, somewhere here, for some nodes, we want to analyze this using like we are looking the reliability with respect to the deflection. So this is, we can have the allowable deflection and the actual deflection. Actual deflection we can get from the numerical analysis, or the FEM code. We have model using the FEM tool we use to model this, we can find it out. Now we already discussed that we can go for the Monte Carlo simulations. We can generate different random samples. Using that random samples, we can perform the numerical analysis of this model. We can get the del every time we can formulate the gx, and we can perform the Monte Carlo simulations. But the task is, if we replace this limit state with some arbitrary meta model, or the using some response surface, and if we can perform the reliability analysis, that actually help us to avoid that huge simulation time. For this kind of implicit limit state, we already have discussed that we can go with the Monte Carlo simulation. How this Monte Carlo simulation will be performed, like you need to perform like here for this bridge. Say let's consider this example for this bridge. So we wish to perform the reliability analysis with respect to the allowable deflection and maximum deflection for some node. So here for some node we create some gx, that is nothing but del allowable. Allowable will come from your tolerance limit, the is will give, or that the specification you are working with, that will give you that value. And this del L star, that means the actual deflection somewhere. Like if you wish to find out the deflection here or here, anywhere you want to find out that deflection, you can find out from the code. Like if you model it using NSYS, you can find out the what will be the deflection of this node first, if these all values are deterministic. Now if you wish to perform the Monte Carlo simulation, what do you need to do? You need to create or generate the samples, or different samples, like 10 to the power 5, 10 to the power 6, how many to converge, you need to figure it out. So you need to generate this. Like for example, P. I'm generating 100 samples of P. So 100 times I will run this code, and 100 times I will get del star. Say for this point, I will get the 100 del star. Del allowable, say for example, del allowable is 0.1 meter. 0.1 meter is very high. 0.01 meter. Okay. Or 0.001 meter. So we will have 100 gx. Then 100 times we will check how many times the gx is less than equals to 0, and we can perform the Monte Carlo simulation. But it will take much time to give you the converse results. So in response surface method, what we do, we replace this limit state using some meta model, and then we perform the reliability analysis. And for this we use that least square curve fitting technique. And how, just we will see. First, what do we do? So first we propose some response surface in term of polynomials. Like here we have proposed that Rx R stand for nothing but the response surface. Here we propose like this model will be a second degree model. A0 plus summation of I equals to 1 to n bixi, summation of I equals to 1 to n ci x square. Recall this polynomial f of x is equals to a naught plus a1 x plus a2 x square, all this. So xi are the basic variables, and here a, bi, ci to n, these are the unknown constant. Now we have the polynomial. You can here, up to the same that cubic feet is considered. You can consider up to nth order as per your requirement. That many number of simultaneous equations you need to develop, and you need to solve for the unknown coefficients. Okay, so first step, we consider one response surface. This is nothing but your meta model we have considered. Now what you need to do here, look, we have how many unknowns? Like if we have two random variables x and y, we will have 2n plus 1 number of unknowns. Like n is the number of random variables. So we need to have that 2n plus 1 number of simultaneous equations to solve that 2n plus 1 unknowns. So how we can have this 2n plus 1 simultaneous equation? What do we need to do? First, we sample that 2n plus 1 number of points. How? So first point is the mean, and we generate or we sample 2n number of points around the mean. So if we have two random variables, so the total number will be 5. That means one will be mean and another will be around the mean. Now how around the mean? Actually mean plus minus k sigma, we use the formula plus minus k sigma to sample these points, and these points are called the support points. So once we have this supports point, 2n plus 1 supports point, just replace this supports point in this meta model. So you will have 5 number of simultaneous equations along with 5 number of unknowns. Solve them, you will get the unknown, and finally you will have the response surface here. So once we need to first we need to propose the meta model, then we need to sample points around the mean. How? Mean plus minus k sigma. K is a constant generally taken as 1 2 3. That means mu plus minus 3 sigma will cover the entire distribution. Like the concept is that, and you just need to formulate that 2n plus 1 number of simultaneous equations, solve for the unknown coefficients. Once you have the unknowns, you can easily formulate the Rx. Now once you have the Rx, now let's say after solving we have getting the Rx is equals to like that, um, say some value 0.002 plus 0.15x plus, say for example, 2.5 x square. Now I have the limit state that Rx response surface. Now I can consider this as my limit state and perform the Reckwitz algorithm to solve for the design points. Now once we have this Rx ready, we can perform the the first order and second order reliability method to get the results. Now here we have another check, like due to the modeling error, many of the time our response surface, like here you can see this is our response surface, this is the original gx, may not fall on that gx. So what we need to do, we need to check or we need to interpolate this with respect to the mean value. That means we need to go one step more. So here the interpolation thing is done. Like once we have the that design values, that means after solving the response surface, that Rx, after solving that response surface, what the final design values will be, that need to be interpolated with respect to mean. How? A simple interpolation, like if you have x1, x and x2, y1, y and y2. So the interpolation says nothing but x minus x1 divided by y minus y1 is equals to x2 minus x1 divided by y2 minus y1. So here x is nothing but that x1, that x1 is nothing but the mean point here. So that is nothing but your g of mu. What is the y1? It's nothing but mu, g of mu corresponding to mu x. This is g of xn, the new design point. This is xn. This is g of xd and this is xd. Now do the interpolation. So what we will find it out here. So x here, for the x you have g of xn minus x1 g of mu divided by x2 minus x1. So x2 is nothing but g of xd minus g of mu is nothing but equals to, here you need to provide y minus y1 divided by y2 minus y1. So xn minus your mu divided by xd minus mu. Now solve it. Here g of xn will be equals to 0 because the xn point, here you can see this point will fall over the limit state, and we know that g of x is equals to 0. So if this goes to 0, now solve it, solve this equation, you will get this equation. Xn will be, this xn will be nothing but this. So that means after getting the final results, we need to go for the extra steps. Extra steps, why? To interpolate the final design points with respect to the design points we are getting using the first order or second order gradient based reliability method with the mean values, so that our response surface will fall over the limit state, and it's kind of check. So how this procedure actually work, we will see. Like for this example, let's see, we have this cantilever example. So for here the limit state is already defined, but for the time being consider, okay, we don't have the limit state, we have only that two variables, random variables here, fy and z. So for the fy, the mean value is given 38, the standard deviation is given. For z, the mean value is given and standard deviation is given. So first what we need to do, first we need to propose one response surface. So let's say we will consider the quadratic approximation, a quadratic fit will go for that. So in quadratic fit we have like a0 plus b1 xi plus c1 xi square. Now here, like if we want to put that n is number of 1 2, here we have 2. So two random variables, so we can easily expand it, like a0 plus b1 x1 b2 x2 c1 x1 c2 x2, because we have only two random variables. So when we have two random variables, we need to generate 2n plus 1 number of data points. So first data point will be the mean mu1 and mu2. So first data point here you can see mean, the actual mean 38 and 54. The second data point will be say mu1 plus k sigma. That means we are generating using mu plus minus k sigma. So let's say k is equals to 3. Here we are considering. So mu1 plus k sigma 1 and mu2. This point, this and this mu2. Now move to third point. Third point will be mu1 mu2 plus k sigma. So this mu1, look, mu2 plus k sigma. You will calculate mu2 plus k sigma, you will get 62.1. Now the fourth point will be mu1 minus k sigma, because here for the first point we consider mu1 plus k sigma. So here that will be mu1 minus k sigma and mu2. So this is the now. So first point is the mean, second point is this, third point is this is the fourth point, and we have the fifth point here. That means nothing but we are sampling the points or the support points we are getting in and around the mean. So mean is the first point and we need the twin points around the mean. That twin points actually generated using mu plus minus k sigma plus minus k sigma. So mu plus sigma you will get used with mu minus sigma with mu2, and another 2 you will get when you flip the arrangement. So here we are getting this much of sample points. Now sample points are generated. Now put all these sample points, you will get 5 simultaneous equations. Here in the second page, that thing is actually done. So you will have gx in a matrix form. If we sum them in a matrix form, so gx, that means 5g, we have 5 points, we will get 5 simultaneous equations. So g of x1, g of x2, g of x3, g of x4, g of x5. That means the size of this will be number of unknown equations multiplied by 1. That factor will continue. Now on the left hand side, what we have? The terms with the coefficients. Like with A, we have 1. With B, x1, 1. B2, x2, 1, and all these things. Like if we go to the previous slide, you can have the feelings like here. Put all these values. So first we will look for the data 1, then 2, then 3 and 4. So we have that 5 simultaneous equations in our hand and the unknowns. So we can easily calculate the unknowns, like D will be nothing but x inverse of G. Least square approach. So we find out the D. Now 1D, that means the vector of the unknowns. That means this one is your A, B1, B2, C1, C2. Once you have all these values, you can now have your Gx. Like just replace these values in your actual polynomial function. Now let's quickly see. This is our the response surface. G of x is minus 3192 54 x1 38 x2. Now once we have this G, now we can convert it into Z space and perform the rest of the reliability analysis using Rakowitz or Rakowitz-Fischler algorithm. And finally, we need to go for the check, where we need to interpolate the final design points with the mean value to have the points on the actual limit state. So the concept is very clear. Like this is the generic one for up to the nth order. We need to consider, if we want to consider up to nth order, then we need to follow this. So the response surface, concept of the response surface is very clear. Like what we need to do first, we need to propose one meta model, that means response surface. Then we need to generate 2n plus 1 number of simultaneous equations. How? We need to sample that 2n points around mean, that means mean plus 2n points. Okay, now once we have these 2n points, we can now have our limit state, that means the response surface. Now once we have the response surface, we can evaluate the design points using form and sum. Now the new center point, at least at the last stage, the new center point or the new points we are getting from the reliability analysis, we need to interpolate it with xd, and we will get the value of the final point. So the algorithm is very simple. First start with it, then first approximation of mu, generate 20 points around mean. That means we already have 20 plus 1 approximation. Then find out the rx, apply the level 2 method to find out the reliability. Now once we have this level 2 method and find out the reliability, what do we need to do? We need to lastly we need to go for one step where we do the interpolation things and all these things and stop. So let's quickly we will code it and we will check that this response surface method is giving the accurate results or not. So for checking purpose, what we will do here also, you can add the cross terms to your polynomial function. We will see that we will make a general code where that cross terms are also been or will also be included. Okay, so let's say we will first code, let's code it and we will solve this problem. Already we have solved this problem using using form and sum, and we will check whether we are getting similar kind of result from the response surface method or not. So first, what do we need to do? First, we need to code this algorithm, right? So what do we need to do? Let's go and let's see how we can code it. Okay. So the concept of response surface, I think clear. What we are doing in response surface method. What we are doing? We are actually first proposing one meta model. We solve for the unknowns, create the meta model. Now using that meta model, solve the second order reliability method. Now once the second order reliability method is done, the last step is like we need to interpolate these points with respect to mean to get the best convergence. Okay. Now so this code actually this function file is generic. Also consider the cross term. So we'll see in a minute. Okay. So let's check one by one. So 1 second. Okay, so this is the actually function file for response surface method general. So you need to give the input mu, sigma, k. We will see in a minute. So first, let's see. First, what do we need to define? Okay, yeah. So first, what do we need to define? We will see in a minute, like how we can code it. First, tolerance. We define the tolerance. You can define the number of iterations, and also you need to define the number of iterations you need in the requisite algorithm, because we have already seen that once we have formulated the response surface, we need to perform the requisite algorithm and all these things. So first, what you need to do, you need to generate 2n plus 1 number of points around the mean. Here you can see, like we can we need to generate that 2n plus 1 number of points. So first point will be the mean, and then mean plus minus k sigma will give us that rest of the 2n number of points. So here precisely we are doing that. Like first 1 to 2 into nrb plus 1 excess into 1 regret point, first regret point, second regret point, and that third point. Like we generate here 2n plus 1 number of support points. First support points mean, second support point mean plus k sigma, and third support points, that means set of supports point, mean plus minus k sigma. Now once we have generated these support points, what we need to do? We need to replace this in our limit state function. So we need to provide the limit state separately. Here we already have seen that we actually supply the limit state using another function file. Like here, for the problem, we are solving this problem, or we wish to solve the cantilever problem here. So we have two random variable fy and z, so x1 and x2 minus 1140. Now feed this like x1 and x2 minus 1140. So this function file, what we will do, if we provide that support points, it will um, you know give you that much of simultaneous equations from your limit state function. Now once you have this limit state function or the support points and the limit state function, what you need to do, you need to first formulate, or you need to first calculate the coefficient. So just a few minutes back we have seen how we can calculate the coefficient. So and we made the code for the response surface, that least square method. There is nothing but that xm inverse of that g, that means that a inverse of b, what we have solved just few minutes before. Now once the coefficients are solved, what do we need to look for? Once these coefficients are solved, we need to look for the gx. That means up to this step our limit state has formed. Like here we have the response surface. That means Rx we have formed in terms of the coefficients. That means we have the Rx in terms of the basic variables and also some coefficients, like say 1.11 plus 2.3 x1 plus something 2.32 x2 and in this term. Now once we have this response surface, what you need to do, you need to perform the Require's algorithm to get the beta. That means the gradients and all these things. So here, if you need to do the equivalent thing, standard normal to or different kind of variable you have, you need to convert it into standard normal variable, that or equivalent normal variable. So these equivalent things have done, and finally we are having the results here. Yeah, so first we consider this thing and we get the GD. Now we need to interpolate this function with respect to the points we are getting from the second order or first order reliability method. We need to interpolate it, and interpolate formula we have already seen, and why we need to interpolate it we already have discussed. Why we need to interpolate it, like to get the point on the limit state. So it's sort of a check which will direct us towards the convergence. Okay, if you perform this step, the results will be more converged. And now once this thing is done and the convergence of beta is achieved, we are taking the results as beta is bit and the pf. So this function file will give you the first the coefficient value, and then the response surface, the interpolated design points, and finally the beta and corresponding probability of failure. So if we wish to check these function files with respect to the problem whatever we have, so let's quickly consider this problem and verify it, like we are having it or not. So here we have two random variables fy and z. So we need to supply this. So what this function file will do, you need to supply mean sigma k, that means mu plus minus k sigma to generate the supports point, the k you wish to give the input. Like k value is generally taken as 1, 2 and 3, because up to the k, that means mu plus minus 3 sigma will cover your entire domain of this failure. That index we need for the equivalent things, tolerance, and number of iteration and all these things. So let's say we are yet to solve this problem, and we are solving it now. Here the cx value and mu value you need to provide. What was the mean value for this problem? We have two equations, two random variables, so we will have 2 mu. One is like like 38, 54, 3.8, 2.7. 38, 54, 3.8, 2.7, and all are the normal random variable. We need to define the limit state x1, x2 minus x1, x2 minus 1140. Now let's call it. Now giving after giving all these values, I am calling my RS that response surface method general code, and I want to check the results. Now run it. What will you do? It will first create that polynomial. Then depending on your variables, it will create that simultaneous equation, solve for the coefficients. Once the coefficients have solved, it will create the response surface, perform the second order reliability analysis. Finally, it will do some interpolation for the final design points with respect to mean and give me the results. So let's check what the results it print. So the beta, it gives me 4.26, and precisely we are having the beta 4.26 using the first order reliability method, considering the actual limit state and this here. So here you can see the first iteration. Visually you can see the first iteration we have these four support points along with the mean. Then in iteration 2 we have these four support points along with mean, that means total 5. And after third iteration we are actually converts to our value. So these are the three iterations we use to convert this response surface to the actual limit state whatever we have provided. Now you can check different kind of problems like this problem. This problem is directly taken from the Haldar and Mahadevan books. So here they have these values. So if we wish to perform it using the response surface method, let's check whether we are getting the results and not. Already your course instructor have shown this thing. So already this will going to convert. So that is not the big issue. Like let's check mu z equals to 5.4. The difference will be only in 5.4. 2.7 instead of 2.7 you just need to put it here 5.4. Now let's check it. And I hope all the variables are normal. I think two parameters, reliability with two parameters, yeah, normal random variable. So actually I need to look into it what actually the problem is. So it is giving the nan value, but for the previous problem the code is giving the same value 2.7. If I consider that is a 2.7, it is giving the same value like 2.7. Where is the 2.7? This, yeah, it actually give the same value. So I need to look into that. What is the problem here? For this problem, then I will get back to you. What is the problem? Like this is a generic code which consider the all cross terms, but for that problem, why it is giving the nan, I will look into it and I will check why it is giving nan value. And for the other problems you can also check whether it is giving the same values or not. I hope these two normal variables for 5.4, one is normal and one was log normal. I actually not completely remember the thing. Like the second variable is I think log normal. Let's check once, otherwise we will see it later. Not actually the values. There are some problem with the values, I hope. 3.8 and 5.4. 3.8 and 5.4. Okay, I will look into it. What was the problem and why it is not giving? So the concept, I hope this is clear, like what we are actually doing in the response surface method and least square method. All these things we have gone through, that we have already have that polynomial code. We just need to incorporate in this, so it will solve this issue, I hope. So this was the like all about how we can solve the response surface method and all these things, and uh, this or how can we can solve the second order or first order reliability problems if we don't have um, the limit state in the closed form, or in explicit form, or explicitly defined in terms of the basic variables. Okay, so let's quickly solve some problems, then we will discuss. Okay, Abdul, have you gone through the solutions of this week?
Yeah, I've gone through it. I'm just stuck on question number 8. That's it. Assignment number 8.
Question number 8, what that question number 8 says, like we will go into the question number 8. Okay,
Orthogonal polynomial.
or orthogonal polynomial.
Uh-huh.
Okay, so let's quickly discuss about some orthogonal polynomials. So, sometimes about the orthogonal polynomials. Like, what are they? What are the orthogonal polynomials? Like, we have seen the least square approximation. In least square approximation, what we have seen, that we need to minimize this sum of square of errors, and this is nothing but your yi minus the function you are considering, say a naught plus for the linear fit a1x. Now, if you have this kind of thing, so then you just square them up, sum them up for I is equals to 1 to m and these things. So and this polynomial like y is equals to, or f of x is equals to, what we are considering, a naught plus a1x plus a2x square dot a1 or an x to the power n. Now, what we have seen, that to deal with that, or if we want to work with that polynomial, we need to solve 2n plus 1 number of simultaneous equations. Now the question is, like, can we reduce that number of equations? Yes, and that is precisely done using the orthogonal polynomials, using the orthogonal properties. Like, what are the orthogonal properties? Like, I is equals to I. If I is equals to I, then you will get the value. If I not equals to j, you will not get any value. Like orthogonal property, like if I multiplied by fj, if your I not equals to j, it will get you 0. And if I equals to j, it will get you fi or fi square, right? So half of the simultaneous equations will be reduced. So what was the uh, you know polynomial form for this ordinary least square method? A naught plus summation of ai xi summation of bi yi and all these things. So instead of x, we consider here a polynomial function. It's a function. Let's see, it's a function. So considering the same concept of least square approximation, we can find out the sum of square of error here, nothing but with respect to weight also. So weight multiplied by, this is your observed value, this is the polynomial you wish to fit. Now here, instead of polynomial, we are the x term, we are considering itself a function. Now we will look into the function and see what property of this function we can use for the calculations. So with respect to weight function, this is your SSE. What you need to do, you need to minimize it. That means you need to differentiate with respect to the variables and equate to 0. Yeah. So you will get this equations just like least square method, what we have just discussed. Now look into it. If we now impose the orthogonality property, weight function f p of p, f p of q is equals to, if p is equals to q, it will be 0. Not equals to q, it will be 0, like basic orthogonal properties. And if p is equals to q, you will have this square term. Now here look at this, ai, when ai will be equals to aj, then you will have the values, otherwise all the term will get cancelled. So here look into it. we only left with only I terms. That means one term, ai into summation of weight function into fi square dx and weight function into y into fx. Now if you solve for ai, you will have this handy and simple equation, and we don't need to solve for that much of simultaneous equation. So ai are the nothing but the unknown coefficients, and we can easily solve using this function. Now here this is called the orthogonal polynomials. Orthogonal polynomials, that means different kind of polynomials or modified polynomials we can say. Here we can say we have Jacobi, then Legendre, Hermite. These three polynomials are very much useful, or very often we use them. So every polynomial have some domain and some functional form. So this is the functional form, and first we need to evaluate this functional form. How we can evaluate this functional form? This is also very easy task. Like first, f not 0, we need to consider this as a 1. Now we need to find out the other term like f1 x. So it will be have leading term x to the power 1. 1, this is the order, plus we have some constant or some values. That means k 1 comma 0 f naught 0 into x. Now that 1 is nothing but the order of the polynomial, and 0 the constant to which this constant is attached, like f naught. So here we are considering the orthogonal property of f1x to f0x. So first we have this equation. Now if we solve this equation, we can have this. Now if you go to the second order, what we have, that the leading term like f2x, what will be the leading term? X square, plus what do you have, k20 into first f naught x and all these things. Like here you can see first term x square, then 2 0 2 1. Now if we have 3, like f3 polynomial, if we want to consider f of x, like x cube the leading term, then k3 0 f naught 0 plus k3 1 f1 x or 0, whatever you want to consider. So we are getting with x, so x plus k like 3 to f2x. So here we are considering the orthogonality between f2 and f3, and using the orthogonality property we can find out the k. Once we have the k value, so easily we can say that okay, my first order polynomial f naught will be this, my second order polynomial f2 will be this, my third order polynomial is this. Like if we solve one example here, like we have one polynomial function, orthogonal polynomial f1x. Now its domain is -1 to 1. What we need to find out? We need to find out the first four polynomial. Like first you need to do f0x, you need to calculate f1x, you need to calculate f2x, and you need to calculate f3x. So f0x first term will be 1. Now f1, you need to impose the orthogonal property between f1 and f0. So f1 x will be x naught, that means f1 the degree, so x to the power 1, k to the power 1, k that will form one matrix where k 0 1 k 1 0, this all terms will be made. So this is nothing but your degree, and this is the term along which the coefficient is sitting. So f0x, now the second term x square, k20, k, k21, and all these things. And k20 and k21, either you can solve this equation, you will find it out, or you can remember the generic equation ki1 is equals to this minus of integration of weight function x into that functional form. Now here look into here, like
Excuse me. Sorry. Just a
yeah,
minute. Yeah. Can you please go back to this equation? Yeah, I believe this equation was wrong. I mean, the fi should have been f1 in this case, in the numerator and denominator.
yeah, yeah,
Yeah,
yeah, yeah.
I think that during the class.
ki1 is equals to no, it's okay.
Is it fine?
Yeah, it's fine. One, it's one. First term you will get one, like one for one term. For 1 0, like one, it's like one is wrong here. You need to impose some j or thing, and j should be from 0 to n. One we cannot write like one. It should be j, and j should be some value. Yeah, wrong, partially wrong, you can say.
Mm.
Like j should be from 0, like when we are imposing that orthogonality between 1 and 0, so we will have k10 term, right?
Mm-hmm.
So that should be I into j. Yes, j should be there, and j should be ranging from 0 to the values, the order of the values we are looking at. Yeah, yeah, you just make it correct. You just solve this equation, you will get the generalized form of this.
Fine.
Okay. So like K20, you can have K10, you can have K30, like zeros. If we go to this equation, like we don't have zeros, K1 directly have. So that should be some arrays, and that should be arranged from one point to another point, like zero already. Now first thing, when we are considering the orthogonality between F0 and F1, so that term will be K10. So you just
Um, Excuse me, I'm really sorry for disturbing you in between. If we, for example, if we take this equation that is mentioned over here that you just showed, right? If you try and relate it to the problem that we are discussing, the first four orthogonal polynomials one.
yeah,
Yeah. So I believe, for example, take the formula of k1 comma 0
yeah,
equivalent to integration of -1 to 1 x dx. Fine,
yeah.
the numerator.
Yeah, the
So
weight
x,
is one.
the weight is one. Perfect.
Mm.
The x that is shown over here is, as per the formula, it is x raised power I.
I.
Is
Yeah,
it?
yeah,
Huh. And the next thing, f of I, which is shown in the formula,
yeah,
f of I has been taken as 1.
yeah. F1 of x.
F1 of x.
Yeah.
So that's what I was confused about. Like if I write the equation like this, the
Okay.
previous the
Okay.
previous thing, please.
Okay.
Ki comma 1 is
Mm.
equivalent to integration of minus a to b x
Yeah.
raised to I w of x
Yeah.
f1 bracket x.
Yeah.
Yani f1 x. Would that be fine?
Yeah.
Okay. So I mean to say, instead of fi, it should be f1 to make things.
You can think like that also. Yeah, I get your point. Yeah. Yeah. Yeah.
Yeah. Okay. Thank you.
And
That,
I'm saying in another way, like if considering two dimension and make it generalized. Yeah,
oh,
that is also correct. Yeah. Yeah.
okay. Thank you. Thank you.
Otherwise, you are not getting this numerator and denominator in this form.
Exactly.
Yeah.
Exactly.
And you cannot solve this f1x and f2x and f3x, all these forms. Yeah,
Ah.
yeah, yes,
Okay.
yes, yeah, that can be the case.
Thank
Okay, so let's quickly solve our problems one by one. Okay, so the concept, like you can go through this orthogonal polynomials, like they are very helpful when we are going for any least square approximation and we want to reduce the number of simulation time. So very often we can use, or we may use these things or not. Okay, so the first problem, let's see what is the first problem. The length of the bar already given, so we already have solved this problem just a few times back. What you need to do, you have two unknowns, so you need to develop two normal equations. So first normal equation will be summation of L equals to A summation of T plus B n. Second equation will be summation of L T is equals to summation of A T square plus summation of B T. So you just need to solve these two normal equations to get A and B. So to solve this, what you need to find out? Summation of L, summation of LT, summation of T square, summation of T. So you just made a column, a table, and you just solve it. T square, TL. Summation of T, summation of L, summation of T square, summation of TL. Now put these values in these two normal equations. You will have this first equation 160a plus 4b 44, and this as second normal equation. Now solve these two equations, you will get a and b is equals to this. So have you solved this problem and getting the same results? Are you?
Yes.
Yeah. So then okay. Now go to this second. Here like weight are given. So same problem. You just need to multiply the weight with respect to this. So summation of, here also you need to have two normal equations. You need to generate two normal equations, and you need to solve them. So here also just you need to multiply the weight corresponding to the particular thing. So you have this as your first normal equation, this second normal equations, put all these values, you will have this first equation, this second equation, solve them, solve for a and b, you will get a as 3.2 and b is 1.82. So same, I will solve it. Same
Yes.
thing like matrix operation, just go to MATLAB and perform it and leave it. Okay. Now the third problem, a limit state is given as a form of x1, x2 minus 1150. X1 follows normal distribution, x2 follows also normal distribution. Which of the following will be the generate sample points x1 to find the first approximation of the limit state function considering k is equals to 2. Which of the following will be generate sample point? Which of the following? Okay. Okay. The question is incomplete actually. The answers should be given. That means how you can generate the sample points for this thing. So what was the formula or what is the rule for it? Mu plus minus k sigma.
Yes.
So mean plus minus k sigma, k is given 2. So first value will be the mean. Then the rest other 2 and 2 values will be plus 1 minus 1. So mean value is given as like 55 and sigma value is given as 6. So first value mean 55 plus minus. So plus 2 sigma will give you 67 minus 2 sigma will give you 43. So here the x1, they have said that you should use x1 to generate sample points. That means the first sample points will be the mean. That means the 55. The second sample point will be mean plus that means 67. Mean minus 3 sigma 43 for one set. Again for another set you will have that much of numbers. Okay. That means total you will have 2n plus 1. That means 5 number of sets. So here they are asking for only x1 sample points. So you will have 63 and 43 because 55 plus minus plus 2 sigma minus 2 sigma will give you this 2. Actually, they are not asking to generate the complete set of support points. Okay, clear? If
Yes.
they said that complete set of support point, what will be the complete set of support point? First support point will be 55, 33. Second
Hmm.
support point will be, if I consider this mu, that will be mu plus 2 sigma. And this will be mu plus 2 sigma. This is mu. And mu minus 2 sigma. This is mu minus 2 sigma. Just mu 1, mu 2, sigma 2, mu 1, sigma 1, mu 2, mu 1, sigma 1, mu 2, and all these things. So that will be your support point, 5 support points. 1, 2, 3, 4, 5. Clear? Now move
Yes.
to this. Which is the following interpolation formula used to find out? Simple interpolation, linear interpolation, this one. Like x minus x1 divided by x2 minus x1 is equals to y2 minus y1 divided by sorry, y minus y1 divided by y2 minus y1. And you just need to put it all these things, 3 points you have, and you will find out that g of xn that will be 0 because it will fall on the limit state. Like if we have x1, x, x2, y1, y, y2. This is your xn point, xn. This is your xn. This will give you g of xn. This is your g of mu. This is mu. This is g of xd to final design points. This is xd. Now put these values here. You will find it out. Your xn will be 0 because that final point will be on the limit set. Now just replace this all these things. Let's say x minus x1, that means x is g of xn minus g of mu divided by x2 minus x1, right? X2 is g of xd minus g of mu is equals to, on the other hand side we have y minus y1, that means xn minus mu divided by xd minus mean. Now your g of xn will be 0. Now why g of xn will be 0? Because the final point will lie on the limit state, and limit state g of x equals to 0. Now solve it, you will get, simplify it, you will get this equation. Simple interpolation. Okay, so here that thing has actually given. Now you have the limit state, x1 follows normal, x2 follows normal. The obtained design points are x1 and x2. Okay, the new center point of x1, you need to find it out. So your xd is given like 33.5 and 30. Mu are also given, mu are 35, 29. So you need to find out xn. So directly put in this formula, you will get this, or you can do the interpolation also. So you check this with the results.
Yeah, it's the same.
Yeah,
I'm getting
same. So it's not to worry. Now here the problem of your that problem. You have one orthogonal polynomial. The range is given. Weight function is also given. So f naught x is 1. F1 x leading term k10 into f0, k10 minus integrate x dx into this will give you 0. So f1x will be x. Now for the second polynomial, the leading term will be x square, then k2 the order, and this is 0 for along with its sitting. Now k21 the order, f1x. Now solve it, k20 x square in the numerator and x dx 1/3, k21 this will give you this, and finally this. So clear? Just go through it, you will get it.
okay. Thank you.
Okay, so yeah, select the correct statement. Give me the correct statement, Abdul. Tell me. The response surface method aims to replace the original failure function by an equivalent function. Is it correct?
The response function aims to replace the original. Yes.
Yeah. The response surface method is more computationally efficient than Monte Carlo simulation.
True. True.
True. Monte Carlo simulation is more computationally efficient than response surface method.
No, false.
Yes. For the first approximation of the limit state function, mean vector is used at the center point to generate the other sample points.
True.
Yeah. So only the C is wrong.
Not correct. Yeah.
And actually, do we have another any kind of, yeah? So number of simultaneous equation for calculating coefficient for the response surface if we have n number of variables, n plus 1. What was the interval for Hermite function? Hermite
Minus
function minus
infinite.
infinity to infinity. So that's all
Okay.
for today. So we will meet on next session. So Abdul, your that Monte Carlo simulation problem has solved. You
Uh, mm, Honestly, no. I'm actually confused. Both of the formulas work,
okay?
but the one.
Okay. Just tell me, what are you looking for? You are looking for some results. You need
Yeah, I
somehow
have.
to get convergence, like
Yeah, I have FORM and SORM results with me. The
good
beta value.
convergence, and actually the formula that Professor Unas Chakraborty has told you, and also the book I have shared, that Chui and Gandhi.
Yeah.
Yeah, so if you wish to find out some with respect to some probability of failure, target probability of failure
Mm-hmm.
with some confidence interval, you need to simulate this. Like, have you gone through the last that Monte Carlo simulation interaction session? I have actually demonstrated that that the number of samples, if we reduce it, actually what I have done, like I fit that number of samples to the actual PDF and check whether the numbers are getting I'm correct or not. Like I'm checking with the number I'm getting from the search equation n 10 to the power something. Now I am increasing or decreasing the number and plotting the that actual PDF, and
Uh-huh.
checking whether the that PDF from the histogram of the generated sample and the numerical PDF are matching or not. If match, then your result is conclusive. Okay.
Yeah, actually, I'm getting the converged results with the former formula as well
Okay.
that I shared with you.
Yeah.
So that's the thing.
Yeah, actually that one also. But if I simulate, with less number of samples, then you will not get the number of samples. Like if you have lower value of probability of failure, then you need to go for higher numbers. Like
Uh-huh.
it's not actually like that approximation what honestly sir I said, like this might not be the case. Like you will not get the convergence with that. Also there is a one problem we need to look into it. Like when you are generating the random numbers, you need
Yes.
to look into the seed. Otherwise, when you run again and again and again, it will give some different results. So if you can save the seed of the random number generator in
Yeah.
the first case whatever using, then I think you will get the more accurate results. Or I suppose like you should meet with me online and share
Sure.
your codes, and I will check it that. And I also have uploaded that thing how you can plot numerical and check all these things. So like how much number of simulations with respect to that probability of failure you need to go with that equations. I also look into different kind of research papers and books, and also discuss with sir that this. Otherwise, how you can incorporate that confidence interval thing, like how I can say okay this probability estimation with the MCS is lie within that confidence interval. I cannot say, and the confidence interval actually increases the number of simulations, right?
A
N time.
lot, a lot, a lot. It increases a lot.
A lot, a lot.
Most
And if you
times.
check the problem with lower probability of failure, you require more number than this prescribed also. Some more number 10 to the power some tens. So you just need to check it. And that formula which is giving the less number of thing, if you when you are performing the structures or performing the reliability of the structure which have less probability of failure, then the result will not get converged.
Okay.
Okay. So stick with that, and MCS like for the normal. Okay, tell me your model first. What model you are working with?
Yeah.
How many degree of freedoms are there, and how many like
Actually,
random
what
samples?
actually what I'm working on is a slope stability problem.
Okay.
It is not specifically a structural problem.
Okay, no issue. So
Ah,
slopes are also one kind of structure, na?
true, true, true.
Yeah.
So
So you need to make the mathematical model for it. Uh,
yes.
so
So my basic mathematical model is not very complex. It is kind of time consuming, but not very complex.
no. I just want to like is it a linear model or a nonlinear model?
It would be a non-linear model. It would be
No,
a
no issue with the nonlinear model. You have if you have the model, then we can perform it. Have you performed the reliability analysis like using
yeah.
Monte Carlo simulation?
Yeah, I did it. I mean, I'm getting values which are close, like FORM. What I'm basically trying to do is, I was trying to compare FORM, SORM, polynomial cross expansion, and Kriging spaced MCS with the conventional MCS, and trying to figure out which would work the best, since FORM, SORM are gradient based methods, right?
Yeah.
So MCS is the traditional method, and it is the most time consuming method. I would
It's
say
not
that
traditional method. We can say that MCS is your simulation based technique. Simulation. We
oh,
are simulating.
traditional in the sense that taking it as a benchmark.
Yeah.
Authors before me have.
Not.
Huh,
Just don't use that traditional simulation based technique. Yeah.
okay, fine. As a simulation technique, I take it as a benchmark technique. Benchmark as in whatever value I'm getting from
As a
MCS.
benchmark, need to be benchmarked fast,
Okay,
right? That the values of the benchmark model should be benchmarked first. Like if you run this model using lesser number of for the time being, we don't know the how many number we require.
okay,
You perform it. So how you can say this benchmark model or the result of the benchmark model are benchmarked actually. So first you need to work with that benchmark result. Okay, I am looking for this result using form sum or other gradient base or any
true,
other
true.
or polynomial chaos expansion. It's a good thing
Mm.
also. So how we can do this? So just need to look into the model also. Okay. So one day
Oh,
we will sit and we will discuss.
fine,
Okay.
fine, fine, perfect. That would be great.
So okay, then we will close it today. Thank you.
Okay, thank you, thank you.
Thank you.